Hello, Chemistry 2330. We're going to continue on with Chapter 9. This is going to be Chapter 9, Part 1A. So we're going to talk about benzene and its derivatives and what makes benzene different from other chemicals we've been working with so far. So the first thing we need to think about is that back in 1882, there was a lot of chemistry and a lot of chemical industry that was happening specifically in Germany, and they were trying to figure out what was really going on with chemistry. And so one of the things that they came up with is the idea that certain compounds like benzene and other aromatic compounds, as they were called, behave differently than their alkanes or alkene derivatives that they thought that they looked like. So one of the first people to kind of come in and attack this problem was Kekulé. And Kekulé decided that they knew that because of the different number of carbons and everything that we had in our benzene ring, that Kekulé came up with the idea that, well, it can't just be double bonds, alternating double bonds and single bonds, because this 2-1-2-1 just doesn't make sense. It doesn't react like other alkenes. And therefore, he came up with the idea that they were flipping back and forth, so that the ring itself would oscillate and get bigger and smaller and bigger and smaller. And so this actually explains some of what was happening, but didn't account for all of the unusual chemical reactivity. So what we did was move on a few more years up until the 1930s, and the idea of atomic orbital hybridization seemed to come into play, and they were actually starting to understand the difference between sp, sp2, sp3 hybridizations, and so that came up with some other ideas that related to resonance, okay? And in resonance, they were able to explain some of the interesting properties of the benzene ring. Some of the things that they were able to understand is the idea that all of the hydrogens have the same bond length, right here with the carbons. All of the carbons in the system had the same bond length. And they were also able to determine that all of the atoms in the benzene structure had the exact same 120-degree signal. So that's telling them that, number one, they had a very regular structure. All of the atoms were identical, and they all had the same hybridization, and they all had the same energy. And so this led them to, knowing that we had an sp2 hybridized with a 1s orbital, and then this was sp2 bonded to an sp2 bond because of the bond lengths. And so this started to give them some ideas onto, okay, so these are all equal, but how is that possible? So move on a little bit more. How is this possible is the idea that we have orbital overlap of the different bonds. And so what they were thinking, instead of just having an isolated double bond here and an isolated double bond here and an isolated double bond here, that maybe they don't actually have that type of isolation. Maybe instead we think about the system as, well, okay, we have a double bond here, but then we have a partial double bond here, partial double bond here, partial double bond. And so that these bonds are just going around and around and around. And instead of just flipping back and forth, like in the Kekulé model, where you would see the actual expansion and contraction as the double bonds became single bonds and single bonds became double bonds, the fact that there was no oscillation told them that they had a perfectly shared set above the ring and then a perfectly shared set below the ring. And if they're perfectly shared like this, that means that all of the 6 p orbitals that are above and below that ring form a continuous equal pi cloud. And that equal pi cloud is where we get the concept of aromaticity, and it's all because of those same orbitals being overlapped. Okay, so let's add a little bit more information to this. So in theory, one of the reasons that the Kekulé model doesn't quite work is that we would have this oscillation happening between the two systems, going back and forth, back and forth. And so we would have alternating single and double bonds, but we don't see that. No matter how fast we actually can measure that oscillation, we don't see it. Therefore, they have to all be equal. They cannot be flipping back and forth. So how can we prove this? How can we put in our mind that this is really true? Well, one thing we can do is look at it as, well, if they all are isolated double bonds, then we should be able to measure their stability. Okay, so let's think about that as a function of energy. And so if they're not equal, if they are not equal. They're all going to have a different energy. The double bond is a higher energy than a single bond, and therefore we should be able to measure the difference. If not, we can actually measure that whatever stability there is by having them theoretically overlap altogether. And so one way to estimate that is to look at benzene as a function of the heat of hydrogenation compared to cyclohexene. Okay, so what would this look like? So if we take cyclohexene right here, and so it just has the single double bond and it's isolated, and we take hydrogen and a catalyst, we can hydrogenate it down to the cyclohexane. And cyclohexane is the more stable compound, okay? So the relative difference in energy between the cyclohexene and the cyclohexane by having this double bond is 120 kcals per mole, kjoules per mole, sorry. Okay, so that means that when we calculate that and we actually look at benzene, when we measure benzene, we have 3 of these structures. Notice it takes a little bit higher pressure to get this to happen. So it's a much higher pressure, but we can still reduce it down to the cyclohexane. So these right here are the same compound and have the same energy, but it takes 209 kilojoules per mole to do that reduction. So there's more energy involved in this system, which we were expecting because it has more than one double bond. Okay, so let's look at this graphically, okay, to make it a little bit easier to kind of handle. So if we look at this as our relative energy of 0, and that is basically the energy that we have for cyclohexane, okay? So this is in our relative range, 0 kjoules per mole. It's the most stable on the slide, okay? And then we look at the cyclohexene right here, and it releases this much energy going from the cyclohexene to the cyclohexane, and that's 120 kilojoules per mole, okay? In theory, because benzene has 3 double bonds, it should be 3 times this number here. So in theory, we should see it being this number here, 3 times the number of double bonds we have here, which would be 360 kilojoules per mole, okay? When we actually measured the hydrogenation of benzene, we found it to be 209 kilojoules per mole. So what does that mean? That means that if these were all isolated double bonds, they would have a higher energy than if they were a resonance stabilized system. So, and the energy that it is stabilized by is this 151 kilojoules per mole. So the fact that it is more stable than the theoretical 3 isolated double bonds means that we gain energy by having this delocalization. We have this stabilization with this resonance energy. Okay, so how can we use this to our advantage? Okay, so we can use that to our advantage by actually spreading that kind of delocalization over a wide number of rings. We can do it with just 1 ring for benzene, or 2 rings for naphthalene, 3 rings, and then we can have different isomers, and then this is a total 5-ring system. All of these molecules are considered polynuclear aromatic compounds. So they can have more than 1 fused ring, they can be a variety of different shapes as long as they met certain electronic contributors.